All right then, good morning everyone. Today we're going to cover the most interesting and beautiful examples of path integrals, namely Gaussian path integrals. In some sense, our entire course is going to be built on these singular wonderful objects. And we're going to use as much as we can about Gaussian integrals to learn what we can about perturbative quantum field theory. So before we do that, I'm going to cover two more example path integrals to show you why the word Gaussian would appear when talking about quantum field theory. So firstly, I'll remind you of a formula that we derived in the previous lecture for the propagator for a non-relativistic system. Well, it's really a transition amplitude. So we derived this formula in the previous lecture. When I say formula, you have to interpret this statement relatively loosely. So I'll just write the Lagrangian there because that's what it is. For this transition amplitude for a non-relativistic quantum system. So a quantum system that's built as the quantization of some classical non-relativistic system. So we have this formula for this transition amplitude here. And of course what that means is when you want to work with this, you usually do the following procedure. It's usually the case that you can't work out the value of this path integral just by looking at it. And at some point you'll gain enough experience with path integrals that you can avoid these following steps. So, but before you know what a path integral is going to be equal to, you have to follow this procedure to make sense of this thing. So the first step is to discretize this continuous variable q of t into some discrete variable qj. So you take continuous paths and you replace them with discrete paths. And then you use a formula that does work, namely the one we derived before I wrote down this formula in the previous lecture. And there's lots and lots of integrals to do here. And you discretize this nice integral here into, well, a less than nice sum. But it's something you can work with, so it's not so bad. Oops, k. So that's what we arrived at first when talking about the transition amplitude to go from position eigenstate q0 at time 0 to position eigenstate qn at time t. So you really can do this integral, as we'll see in many examples. So step one, when you're faced with a path integral expression like this, is to discretize. Then do it. And this answer that you get for this discrete thing is going to depend, we'll call the answer I, on epsilon, right? Because you've discretized this nice continuous path into a discrete path. So like this. You've taken some discrete, continuous path and replaced it with some bar graph like this, where the distance between, or the width of these bars is epsilon. Then now you've taken this expression that you don't know what to do with. You've replaced it with something where it's just really a lot of integrals, but they're all integrals that you can do. And you get an answer. And that answer depends naturally on epsilon. I mean, it depends on h as well, but it depends on epsilon. And then the final step is, if you can, take the limit as epsilon tends to 0 of your discrete answer. And then deal with any infinities that you encounter then. So this is like the naivest way to make sense of this expression here in the box that I'm about to draw. Now, in the previous course on quantum field theory, we encountered infinities, but they were of a harmless variety which have no operational significance. So we found infinities, but they were always for quantities that you could never measure in an experiment. There's a question?
Yeah, sorry, I don't understand why we use the product of j in the first expression from the box.
Oh, yeah, the question is, why do we use a product over j? Because actually, they are vector variables j. Sorry about that. Yeah, so the infinities that we encountered in the previous course, and we're going to encounter the same sorts of infinities in this course, always pertain to things that you could never measure even in principle, unless we have black holes. But that we will ignore for this course. And we're going to see that this is no different. The kinds of infinities that we encounter when carrying out a path integral according to this recipe here will be exactly of these harmless, not observable types. And to emphasize that, I'm going to do one key crucial example, and it's this example that will guide us really for the entire course. And that is the example of a Hamiltonian, a classical Hamiltonian, of the classical form. So it's got a momentum term, so there's some kind of kinetic energy, and there's some kind of potential energy like this. And furthermore, we're going to assume later that this potential energy is actually quadratic. So it's a harmonic oscillator. But for now, we'll see how far we can get with our path integral in this example here. So we're going to look at this quantity. And ask the question, what do we get when we substitute in that value of the classical Hamiltonian? Who knows? Yeah, I've forgotten some more J's, haven't I? Yo, question? There's an integral missing. Where's the integral? Oh yes, there's an integral missing, thank you. Should do it correct, thank you. Right. So you should think of the path integral not so much as an integral. So I think this is an important comment that I'll make multiple times during this course. Often the most confusion arises in physics and maths, I guess, chemistry and biology, the natural sciences, and presumably also in the social sciences, when people use the wrong names for things. So, and it's even worse here, right? We've drawn integral signs here, and we've called it an integral. So you're entitled to ask, in what sense is it an integral? So if you know about measure theory, you'd be like, well, okay, is there a measure corresponding to this integral? Is this the Lebesgue? Is this like some kind of Lebesgue integral or something like this? And then you will run into troubles. But the reason you run into troubles is that you're interpreting this completely literally as an integral, which it really isn't. It's a recipe. So if I'd used a completely different notation for this thing, then probably that would deal with 90% of your concerns about this object in terms of a mathematical thing. So if I just wrote some totally different notation here, I don't know, like a triangle with Q's and something in it, and I said, this is an algorithm, then you would probably be happy with it and not want to interpret this literally as an integral. So if I said, you know, U Q naught QA is, let's invent some notation here. Let's make it really weird, yeah? So that it doesn't look like anything that you've done in maths before. I call it QA and B. So if I didn't use integral notation and I said use some other notation for this right-hand side, and I never called it an integral at all, I just said this is a box, and this box, to compute the value of this box, you need to perform an algorithm, then you probably wouldn't be so upset about it. So I want to emphasize that taking this literally as an integral is likely to confuse you and upset you. Whereas taking this thing in the box as an algorithm is likely to be much more satisfying when actually working with the object. So sadly people use notations like this because they're strongly suggestive, and they're useful because they help you remember things. This is the same here. I mean, it does help you to remember the algorithm if you see the integral signs, but don't take it literally as an integral. In some sense, it's a mathematical phantasm, right? It's a mathematical object that does not exist yet. Its sort of existence intrudes itself on our activities. There's no way to really take this literally as an integral, but it's so close to being something that exists in mathematical structures that we're tempted to interpret it as an integral. Now, the crucial example. When our Hamiltonian has this form with a quadratic momentum, we can do more, right? So let's look at our algorithm here. And we realize when we look at this term here, the integrand here, that p occurs linearly here and at most quadratically here. So that's great, right? Because doing quadratic integrals is something we can all do, and we're going to do a lot of them in this course. You know, at the very least, to evaluate this object here, we're going to need to carry out the p integral at least, right? We need to carry out the q integral, but let's do the p one first. And this is a very, very interesting integral indeed. Okay, we're going to do a lot of these towards the end of this lecture. This is a Gaussian integral, right? There's a linear term, a quadratic term, there's an e to the I quadratic. Well, as long as you know about complex integration theory, you're not worried by that. And I'll just write out the answer now, but we're actually going to prove this answer later. I mean, it's something that you should all be able to do without thinking too hard. But for now, I'm just going to write out the answer. And the answer is 1 over some constant that I don't care about. As we'll see, we really don't care about it. That depends on epsilon and q. No, only epsilon. And has the following form. So I'll leave that as an exercise, although, as I say, later today, later in this lecture, we're going to be able to, I'll give you all the formula you need to derive these Gaussian integrals. So the way you do these integrals, of course, is completing the square and changing variables. So we end up with that as our expression after doing the p integral. So if we substitute this into our expression for this transition amplitude, up here, then we're going to end up with something rather nice. Well, nicer. So actually I will write out the constant, just to express its dependence on epsilon. Right? That's the answer we get when we substitute in our Gaussian completion of the square integral. And that's where we're going to stop for now. But if we knew v, there's a good chance we might be able to carry out that integral, as long as v was, say, quadratic. Now, there's another way to write this. Yep.
How do you get the two constants C of epsilon?
How do I get the question is, how do I get the two constants here? There's this one and this one here. That's a good question. How do I get them? Yeah, well, looking at it now, I don't see why I have this constant at the front at all. I guess I just miswrote down the... Oh, wait on. I think there's one... Yeah, Righto. Yeah. No, I think you're right. I think there's no additional constant there.
I guess that you need the 1 over 2p, don't you? Well,
Do we need the 1 over 2 pi? I don't think so. I think that's... So if we look at this expression here, we've carried out this integral here with the pi. Where did I write it? Oh, up there, right. So if one just naively substitutes that into here, it should be that. Unless I'm the 2 p's, I don't see. Okay, well, we're talking about a constant which won't turn out to matter anyway, so I'll leave that as an exercise to check so that we can move on. There's another way a notation we can use for this simplified expression here. We can also write that as we could also, if we wanted to exploit this notation, well, there's no h bars in this course, by recognizing that this is just a discretized form of the action. Well, we saw that last lecture. But now we've gotten rid of the p integral. All right. And now I'm going to point out the not particularly surprising observation that if you substitute v of q, a potential which is quadratic, namely a harmonic oscillator, then you can even do this integral as well, because it's another Gaussian integral. I'm going to postpone the discussion of those integrals till a bit later in this course, a bit later in today's lecture, and instead I want to give you another example that's much more important for us in this course. Now we're going to do path integrals for fields. Okay, you all took my quantum field theory course, or you're looking at the videos, so you know everything about scalar fields, in particular classical scalar fields. I'm not going to waste any time reviewing that material, because you can just click on the appropriate video. But I will, of course, write out the Lagrange density. And the Hamiltonian. For a scalar field. Okay. So far, this is all classical. Now, the really interesting thing that should be on your mind when you see a path integral expression for a non-relativistic system, and now I've written down a classical scalar field, you should be wondering, how is it, maybe it's possible to do a path integral for the scalar field. I substitute in this classical Hamiltonian here for this classical scalar field, and maybe I get out a quantum field at the end. So if you remember in the quantum field theory course last semester, we had to work sort of hard to quantize this scalar field, meaning to guess a quantum theory that would have the right classical limit. We had to impose canonical commutation relations, and we had to check consistencies and so on. Here, we're going to arrive at a quantum Hamiltonian via this path integral prescription here. So it's exactly the same as the non-relativistic case. You just have to be a little bit careful about this extra degree of freedom. But if you just, this is a Hamiltonian, so we had a way of expressing our quantum transition amplitudes in terms of a classical Hamiltonian. Let's just substitute it straight in here. We have some final configuration. We evolve for some time t. And we simply say that that transition amplitude here, suppose our quantum field, whatever it is, starts in this classical configuration phi a position eigenstate, so to speak. We wait for some time t, and then we say, is it in this position eigenstate here? Of course, you know that you have to be a bit careful about these words, position eigenstate, but at the naivest level, maybe we can just simply arrive at this number by this path integral prescription. So what would we write down? Well, just blindly following what we wrote down for the case of non-relativistic systems, we might conjecture that the answer is this. So we might simply just define, and depending on your level of rigor tolerance, you might be already happy with this expression as defining a quantum Hamiltonian H. For those of you who might want a bit more of an argument, we're going to give it to you in a minute. So if there is any hope of this working, then this is fabulous, right? Because all this stuff about canonical commutation relations and so on, we don't have to worry about that. We've already arrived at a transition amplitude just by apparently putting in some classical data and then summing over all paths, whatever this may mean. So of course the devil is in the details. We have to make sense of this thing. But now we have to make sense of that, I gave you an algorithm, right? So whenever you encounter an expression like this, you say, okay, first of all, this isn't a literal integral. What it really means is a procedure, and the procedure is step 1, discretize. Step 2, carry out the lots and lots of integrals. Step 3, take the continuum limit. So I'm going to show you how applying that recipe here does make sense and actually leads you to something that you might call a quantum field theory pretty quickly too. So we make sense of path integrals by this 3-step procedure. Step 1, discretize. Step 2, evaluate. And step 3, take the limit as your discretization parameter goes to 0. And this is no exception. This is something we can discretize. So let's get to it. And I'm actually going to I'm not even going to go through the details because I'm just going to sketch how you might do the discretization. We're going to do this in more details as the course progresses. So if you look at the Hamilton density here, you have to discretize this somehow. And the way we're going to discretize is the field at space-time location x. We're going to replace this, we're going to put a grid on space-time and replace this field with a bunch of canonical position coordinates. So we put a grid on space-time, and yeah. And then I'll draw the picture of the space-time grid. Here it is. So we've put this regular grid on our space-time. We've got, and this grid is of width epsilon. And we've evaluated our field, which was nice, some smoothly varying function from space-time to the real numbers. And we've only evaluated, say, its average in a little unit cell here. So this is, well, I don't know. No, let's just do it the way it is, which is evaluate phi at xj. I mean, you could do it by an average, but this is by far the simplest and naivest way to discretize something. So you replace your continuous function with a list of numbers. This is exactly what you do on a computer, right, when you evaluate an integral. If you have some function of the real line and you want to evaluate numerically the integral, what do? Well, here's your function, and you want to evaluate the integral by the trapezoid rule or whatever rule you like, whatever quadrature. then you discretize your function onto a nice fine grid of width epsilon, and then you just sum up the area under this bar graph by whatever quadrature rule you like. And the stupidest quadrature rule, where you just draw this as a bar graph and calculate the area under the bars, already does a reasonable job of evaluating this integral numerically. So we've taken our continuous function phi, replaced it with a bar graph, a list of numbers, and we just have to take care to be able to discretize all the terms in this Hamiltonian there, this classical Hamiltonian. And then we'll just be able to immediately apply this. We'll have ended up with a classical system, classical non-relativistic system even, that we can apply this path integral to give us a number. So we've managed to discretize the field, but look at the Hamiltonian. There's a couple of different terms inside this field, inside this Hamiltonian. We have to discretize everything. So whenever you see an integral, well, I've told you how to do integrals. When you discretize an integral, you turn it into a sum . Now what else do we have in that Hamiltonian up there? Ah, yeah, we've got a derivative. So the derivative is a bit more annoying. We have to deal with that somehow. So we've got grad phi. We have to deal with this, evaluated at position x. Well, that's something that you are familiar with from calculus. And when we talk about derivatives in calculus, we think of them as limits of finite differences. And of course, this is no exception. So we'll call this grad mu of phi, because of course there's 4 possible directions you could be taking this gradient in. And so one way of discretizing this, and it's by far not the only way to discretize this derivative, but it already gives pretty good results, is you take xj and you add onto it a unit vector pointing in direction mu of length epsilon, and then you divide by the length of that unit vector. That's a pretty reasonable way to discretize the gradient operator. It's not the only way. In fact, this is really the most horrible forward difference that you could imagine. It's pretty, this is an explicit way. It's pretty unpleasant numerically if your system is any kind of unstable. There's much better symmetric differences that you can use, but we won't even need to worry about that in this course. And then, at this point, we have, oh yeah, v of phi. Well, that's easy. You just evaluate v at xj. And And so after discretization, you end up with something that looks like a non-relativistic system, just with a funny Hamiltonian. And this Hamiltonian is quadratic in the variables. So there is a subtlety that I'm skirting around here. I guess. Yeah, I guess I'm not going to be able to get away with this. All right, so I'll have to slightly modify everything I've said. We're going to discretize only space, but not time. That's the problem with this prescription here, is that if we're going to start with a Hamiltonian like that, if we discretize time as well, then we have problems with conjugate momenta. Well, yeah, we're going to have problems with conjugate momenta, so we have to discretize space and not time. So, but this makes very small changes to what I've already written. So, firstly, space, and then we leave time continuous. This is txj, qt. I hope you can do these substitutions in your notes as well without much difficulty. And then everything else I said on that board holds true when the time variable is continuous. Yeah, that's still true. This is also true, but it's just true. And then this is also true. The difficulty is conjugate momenta. You have to be a bit careful about discretizing Hamiltonians. So the Lagrangian, or the Lagrange density, when you discretize the Lagrange density, gives you an epsilon in front of the time derivative. So I'll show you what I mean. So the Lagrangian is the integral of the Lagrange density. And if we discretize, this becomes a sum of a whole bunch of things, but there's there's one term that I'll just leave in. So the crucial term here, the one that plays an important role in discretizing the Hamiltonian, is the time derivative of the field. Everything else doesn't matter for this discussion, but this thing here does matter. And when you calculate the conjugate momentum for the discretized theory, then you end up with a slightly unexpected answer. So the conjugate momentum for discrete position J, well, we know how to work out conjugate momenta, right? You take the derivative of the Lagrangian with respect to Qj dot. And this is none other than Qj dot. So this seems perfectly innocuous. But if you do that, well, what do you get? You get, of course you get Qj dot. But you get something else. You get an epsilon cubed that comes along for a ride. So the conjugate momentum picks up this epsilon cubed. It's in there for dimensional reasons. But if you forget it, then you get the wrong discretization. So I'm emphasizing this because it's super tempting to look at that classical Hamiltonian and to just discretize it, right? To just replace pi with pi j, the integral with epsilon sum, and so on the gradients. But you'll get the wrong answer, and you get the wrong answer for dimensional reasons, or you get the wrong answer because the symplectic, you'll wreck the Poisson brackets. However you want to understand it, If you just naively discretize the Hamiltonian, you're going to get the wrong answer unless you put in this extra epsilon cubed factor. So the discretized Hamiltonian for our field equals epsilon cubed sum j, and now we have to deal with pi j, so half pi j squared gives us an epsilon to the 6. Wait on, is it epsilon 6? Epsilon 3, I think. Minus 3. Plus a half these finite differences. I do believe that's correct. You'll have to check it. There's an epsilon to the minus 3 here, which I haven't written out very beautifully, but so that looks a bit unexpected, right? If you just took the Hamiltonian and discretized, then you would have an extra epsilon cubed factor here that you wouldn't have if you did it properly. Whatever. Now we've discretized. We've really got a legitimate discrete classical system. And we can just do our non-relativistic path integral on this discretized system, get an answer, and then take this continuum limit. So I just say just. We still got to do a lot of integrals, and it's because we're dealing with Gaussian theories in the beginning of this course, we're going to do a lot of Gaussian integrals. So for the rest of this lecture, I'm going to remind you of how to do Gaussian integrals. So before I do the Gaussian integrals, I just want to write down the summary of what we've learned about the scalar field. So for the scalar field, when you do step 1, you end up with a lattice system, which is in non-relativistic form, right? It's a kinetic energy term plus some potential energy term. So H discrete, so H phi gets mapped to H discrete, which looks like some sort of kinetic energy term plus some potential energy term which includes all that stuff over there. And then step 2 is evaluate path integral, which is what we focus on now. And step 3 is the limit as epsilon tends to 0, which is going to come later in the course under the title of renormalization. So I've just drawn down our entire course. We're going to spend almost all our time building discretized approximations to path integrals, trying to evaluate them, and then trying to take the continuum limit. Now, the most important case is when our potential is in some quadratic form. And this will correspond to Klein-Gordon theory in the field case. So when you discretize Klein-Gordon theory, something I encourage you to do, I won't do it in this course, I'll just observe that you get a Gaussian at the end. When you discretize Klein-Gordon theory, you will end up with a potential that looks like this, like some quadratic. And that's wonderful in the sense that that means we've now got, when we try and evaluate here at step 2, we're going to end up with Gaussian integrals. So let's get to it. Gaussian integrals, a reminder. Yeah, I know you know this stuff, but do you really know this stuff? Let's find out. What's that integral equal to? Minus infinity to infinity. Anyone know the answer off by heart? Square root of pi, exactly. Now, I want to see a show of hands. Who remembers the square root of pi? Okay, who remembers how to derive the square root of pi? Yeah, that's not a majority, let me say. This is one of the most beautiful proofs in all of mathematics, so you're going to have to endure it again. Exactly, I'm going to do all these steps. Yeah, you remember, that's good. But I'm going to do it because I think it's good. It's good for your soul to do these kinds of things, to know these proofs. Okay, this is what Erdős would call a proof from the book of perfect proofs. This is easily one of the nicest proofs I've ever seen. So trick 1 is you go, okay, I'm not going to evaluate I, I'm going to evaluate I squared. Why not, right? So what is I squared? Well, I squared is this, isn't it? Whoops. That's I squared. Why would you do such a thing? Well, as I'm erasing the board, I invite you to put those two exponentials together. And what you'll get is e to the minus x squared plus y squared. Now x squared plus y squared is the squared Euclidean distance from the origin of a two-dimensional plane. That should make you think of polar coordinates, which was already suggested. So we're going to make a change of coordinates. We're going to go from Cartesian coordinates to polar coordinates. And because it's still early, I'm going to do all of this. Say x is r cos theta, y is r sine theta. And we've got to work out the Jacobian matrix. So that's dx, dr, dy, dr, dx, d theta, dy, d theta. Why am I doing this? Because I can never remember if there's an r d theta or an r squared d theta or whatever. So we have to, there's no other way except to just work out the Jacobian. And we get the determinant of cos theta, the determinant of sine theta. We get a matrix whose entries are cos theta, sine theta, and on dx d theta is x d theta minus r sine theta, and we get r cos theta. So after all the dust settles and we work out the determinant, we get r. I mean, I think you can do that in your head, right? R times cos squared plus r times sine squared is r. So we've worked out the Jacobian, so now we know the measure for our very nice integral. So it's r dr d theta, 0 to 2 pi, 0 to infinity, e to the minus r squared. Okay, great. We've already done a dimension. We've already can reduce this down to a one-dimensional integral because 0 to 2 pi integral, this doesn't depend on theta. So this is just 2 pi times 0 to infinity of r e to the minus r squared dr. All right. Now we observe that the antiderivative of this thing is something you can work out. This is d dr. Basic algorithm for doing integrals is to express the integrand as a derivative. And what do we have to differentiate to get this? Well, the answer is this. Not quite, right? There's a mistake somewhere. What's the mistake? Well, when I differentiate this, I get minus 2r, which is nearly the same as that, but not quite. So that's the antiderivative there. And then we're done. Because when you work out the integral of this function here, you get e to the minus infinity over 2, which is 0, minus e to the 0 over 2, which is a half. And you get a pi. So I squared equals pi, or in other words, I equals root pi. Well, plus minus root pi, right? If you have to be super careful here. But it was a positive integrand after all, so we know which one to take. Okay, that's the Gaussian integral. Quick reminder. But we want so much more from this integral. We just don't want to know the value of the integral. We want so much more. We want to know all its moments. Furthermore, the integrals that we have aren't in this particularly nice form of e to the minus x squared. They have some coefficients in them. So it's not that difficult to evaluate slightly more complicated Gaussian integrals, but I'm going to do it anyway, because You need to become extremely fluid with these calculations. And it's only by doing lots of examples that you actually get that fluidity. So firstly, the integrals we're going to encounter will typically have the form of, they won't be in this very clean e to the minus x squared form. They'll have extra factors, and we're going to have to deal with that. They're going to look like, this, the kinds of integrals we're going to have to deal with. They're going to have a quadratic term and a linear term. Now, I'll even do the steps here because you've got to get used to this. I know you know it, I know you could remember how to do this, but could you do it straight up without thinking, is the question. Probably, yeah. All right. What do we do, right? How do we reduce this integral to that one that we started with? Does anyone know the words? Yep. It's yeah, it's on the exercise sheet. That's right. So I'm not going to do it. Good point. I'm going to write out the answer and you're going to have to do it. Look at that. That's the answer. Very beautiful. Yep, that's it.
It's just a constant j, not supposed to be the Jacobi determinant.
Oh, thank you. That's a good question. This is not a constant j. This is not the Jacobian matrix j. This is some constant. Yeah, I better highlight that, right? Yeah. Goodness. This is the generating function for the Gaussian. This is an extraordinarily useful object, as we'll see. I'm going to write out two other integrals. Well, no, I guess I just write out one. It also works for complex numbers. There's one other integral which also works, but you need to invoke a bit of complex function theory to really get it to work. But we really need this one, so I will write it out. Here's the integral we're actually going to encounter in practice. It's a complex Gaussian. But there's no worries. You just throw in the I in the appropriate place, and that's the correct answer. Complex Gaussians, just rotate the contour and then you're good. So these are two integrals that we need. In fact, everything in quantum field theory, every single result in our path integral approach to quantum field theory will reduce to these two integrals. So that's the really remarkable fact about the whole path integral approach, is that you can get it all. I mean, there'll be steps, right? There'll be derivations that we have to do to reduce it, but in the end, we'll write out a lot of these integrals, and that will be the answer. Absolutely amazing. Now, what do we need? This is still not enough for us. We also want the moments. What we're going to encounter in practice, as we'll see, we're going to want the moments of a Gaussian integral. This is something that's going to come across, we're going to come across time and time again. So what are these? These are defined as the integral dx, x to the n, e to the minus half ax squared, all divided by the area under the curve. So this is a crucial object that we encounter time and time again. It turns out to be directly related to correlation functions. We need to work out what these things are. So what are these? Well, I've turned the Gaussian here into a probability distribution. That's all I've done here by dividing by this number. And what we need is we need to work out these moments. What are these moments equal to? Well, there's a very incredibly beautiful formula for these moments. I'm going to write out the answer, and I'm also going to show you how you might derive that answer. Firstly, can anyone tell me what the odd moments are equal to? 0, that's right. We only have to worry about even moments, because the integrand is symmetric or anti-symmetric. So, poof, 0 if it's odd. And when it's even, the moments have an extraordinarily nice formula. Oops, 3. Yeah. So-called double factorial. So, how would you prove this? Well, it turns out the answer is in front of you. I invite you to look at the generating function here. So there's at least one derivation of this answer where you can use this, the fact that you know this integral. And I'll give you a hint of how it looks. Okay, if you have to do an integral, then you don't really like that because you have to do this numerically. But if you can reduce a problem to evaluating a derivative, then you have an algorithm. So this is, the way to evaluate this object here is by carrying out derivatives. The idea is you'd carry out this derivative and then evaluate that integral at j equals 0. Every time you do this derivative with respect to j, you bring down an x. And then that corresponds to the x here in the moment. Really fantastic observation. Because we know what that integral is. We've already done it. Oh, and I've forgotten the normalization. Apologies. But this normalization doesn't depend on j, so it plays no role in this calculation. And so you get the answer that, oops. Okay, you're an induction away from the answer. I'll leave it at that. All right, I can't resist mentioning something about how you might argue that. So this number 2m minus 1 is a very intriguing number. A double factorial. So 2m minus 1 double factorial is the number of ways of joining 2m points in pairs. So all science, that's a bit bombastic, but should end in linear algebra or combinatorics. And if you haven't done linear algebra or you haven't done combinatorics, then you haven't done any science. That's a little bit over the top, polemic statement, but there's a grain of truth to that statement. And here, we haven't quite done science because we haven't quite done the combinatorics, but we're about to do it, right? So by observing this, we can attach a combinatorial interpretation to this moment calculation up here. It takes a little bit of work to attach this combinatorics to that differentiation task up there, and that's your task on the homework and more. And so on. Oops. These diagrams, I'm drawing them here, not to actually explain the proof really, but to get you used to interpreting these objects in terms of diagrams. Because you've seen these diagrams before. Okay, this is not an explanation, this is a mystery at this point. Right, that was one single Gaussian integral. Now let's do many. So, for our encore, we're going to take the results we've proved for one Gaussian variable and extend it immediately to a vector of Gaussian variables. And now we're going to end up with combinatorics and linear algebra, so we're really doing something. All right, let x be a vector of real numbers distributed according to some Gaussian distribution. Therefore, we're going to want to be able to calculate this Gaussian integral here. What is this integral? I of a j. Well, is this on the exercise sheet as well? No, okay, so I can do this. Sort of. I'll remind you how we do this integral. So, I didn't tell you something. For a an n by n symmetric real matrix. So step one is to turn this exponent of lots of things into something that looks like something we've done before. So this is, when you see symmetric real matrix, you should think of matrix normal forms. And the normal form for a symmetric real matrix is there exists some orthogonal matrix O, some diagonal matrix D, which allows you to write A as that product there of three matrices. So we're going to use this matrix to define new variables, y, which are ox. Yep.
The j shouldn't be a vector as well.
Shouldn't the j be a vector? Oh yes, it absolutely should. Thank you. Otherwise you've got something that doesn't really make any sense. Good. Let's define now a new vector y according to that recipe there. All right, one can do that. You know what? I'm going to just do this for the j equals 0 case and leave the j is not 0 to u. This is such a good exercise. I don't want to deny you the pleasure of this most wonderful integral. So now we've got to work out the Jacobian, which I'll now write as JAC to not confuse it with the other variables. And then the Jacobian is then just O itself. And the determinant of the Jacobian is just plus minus 1, depending on whether O is orientation reversing or not, which it's not, so we can take the plus 1. So we can do the change of variables super quick. There's no difficulties in doing that change of variables. Oops. And we end up with a most beautiful answer, namely that. So what I really particularly like about this approach to quantum field theory is you don't need to remember anything. So hardly any of this actually appears in my notes. You can do it from memory. Once you know the general proof technique, you don't have to remember Wick's theorem, there's the normal ordered and the blah, blah, blah. You can just remember basic facts about Gaussian integrals and rederive everything. Where were we? I of A for j equals 0. Well, we've reduced it now to something super simple. It's just the product of n independent Gaussian integrals. Where dj is just the diagonal element of D. But we already know how to do this integral. So this is the product of j equals 1 to n of root pi on dj. I think.
One question.
Yeah.
The D, the diagonal matrix,
Yes.
is this the unity matrix, or
No.
why doesn't the eigenvalues don't matter in the integral?
The question is, why don't the eigenvalues of the matrix A not matter in the integral? Well, they do matter, and this is exactly where they matter. So D is a diagonal matrix these are the eigenvalues here, D1, D2, yeah. And so these diagonal entries appear exactly here.
Yes,
Good. So then, yeah, I think that's correct. And this has another name. It's the product, it's the square root of the product of the eigenvalues of A. Ah, but the product of the eigenvalues of A is the determinant of A. So that's the answer. Oh, thank you, yeah. Pi to the power of n. Now, your task is to generalize this to the case where j is not 0. I'll write out the answer, but you still have to do the work. And I actually will have to look at my notes. All right, that one's for free. Oh, yeah, there's a half here. You get that for free. You knew that was coming. But you have to have this as well. That's an exercise. And there's a -1. That's extremely important here. That there's a -1 there, and that you've got a 1 on the determinant here. That's your exercise. It's an additional exercise, and it's one that's so important that you really should do it as a matter of priority. Because everything we do from now on in this course will be built on this generating function here. Knowing the generating function will be enough to do perturbative quantum field theory for all scalar fields. And later on, we're going to do all of this for fermions. I'm looking forward to that part of this course. We'll look at non-commuting variables. And then in the last part of the course, we'll do it all again for gauge bosons. But right now, we are focused on just evaluating these Gaussian integrals, and I'll show you in the next lecture how once you have this formula, you get Wick's theorem for free. But I think I don't have time for that now, so I better stop. So thank you very much.